Okay, I think I'm going to go ahead and get started. So the mic, sounds like the mic is working. So, I'm Brooks Davis, and I'm going to be talking about some work we've been doing to isolate jobs running on our computing cluster to improve performance and to improve predictability of runtimes in that with respect to the performance. So before I go into start talking about the technical issues, I want to introduce the company I work for because that the type of work we do and the sort of users we have affects the solutions we can implement, and what works for us is sometimes different than what works for other institutions. So we're the Aerospace Corporation. We operate a federally funded research and development center in support of national security space, which means we work for the U.S. Air Force and the National Reconnaissance Office. We basically do anything related to space systems. We don't do manned flight. We're not involved with NASA at a very large scale, but we work with all of the DoD space, and we do a small amount of civilian space as well. So we're over 2,400 engineers, probably closer to 2,500. And as I say, we really do cover the whole problem space, including things you might not think of as space related. We do a lot of networks, we do a lot of ground systems, we do materials science, largely looking at things like, what sort of materials do you need to make bearings that'll last for the lifetime of a satellite, because it's really bad if the solar panels don't move anymore. Things like that. And all these engineers run different applications of different sizes, ranging from little spreadsheet things that they've developed to a lot of MATLAB applications, literally spending millions of dollars a year on MATLAB, and then up to larger traditional parallel applications, including things like CTF, which is an explosives model that's used at many labs. Our current primary high-performance computing resource is the Fellowship Cluster, which I've given a number of talks about. It's a 352-node cluster. Each of those nodes is 2 processors of some vintage or another, either AMD or Intel, ranging from single cores up to quad cores. So we have just shy of 1,400 cores in the system. There's a gigabit Ethernet network that connects them all. Previously it was a single switch. These days it's actually now 2 Cisco 6500s connected into VSS mode, so it's one giant switch, and currently running FreeBSD 6. We'd like to move to 7 sometime soon, in particular so we can actually implement some of the things I'll talk about later in production. We run Grid Engine Scheduler, one of the 2 main open source schedulers, the other one being the Torque and Maui combination. And small amount of storage, a few terabytes. And then we're also in the process of building a couple other clusters and bulking up our large SMP systems. But really, Fellowship is the majority of the cores available. So, quick outline of the rest of the talk. I'm going to make the case for why we need to do resource sharing within the cluster, and then talk about the problems a little bit, and then look at some of the solutions that are available to those problems that are either typical solutions or some newer things, and then talk a little bit about our experiments. So the main case for resource sharing is simply that we can't just give one user all of the cluster and they can do whatever they want with it until their task is done, because we have these 2,400 users all doing very different things, many of which are doing very different things. And we also have many users who come along and say, okay, they're not doing anything for months and months and months, and then they'll say, oh, I need 10 CPU years, and I need it now. So we can't afford to just buy everyone a cluster. So they all need to be using the same resource. Users also demand, in many cases, partial results, especially when they're doing these very long computations. And so if we have one user who's using all of the system, and this other user, needs to sort of sanity check their results by looking at the partial results or see if the solutions are heading in the right direction. They can't do that if they're blocked out. So we need to have an efficient sharing mechanism within the cluster. Problem is, of course, that resource contention happens. Users will need the same thing at the same time. That is, of course, why so that's a big issue. And some jobs also use more resources than they request. So they can say, a badly behaved job might say, I want to run on one core on a machine, but then they fire off a multi-threaded application that takes up all 8 of them. And so if there's no enforcement mechanism to contain that behavior, that can cause problems for people on those systems. So it can make it difficult as a result of those sort of contention issues. Job completion time can be difficult to predict. If you're on a machine and you expected that you were getting 7 of those cores, and somebody else comes in and tries to run on all 8 of them, you're going to get probably about twice the runtime, possibly much more if you get driven into swap. And so that's an issue. So I'm going to talk now about how different ways of addressing those problems with sharing. One of the most common methods, it's used by many large supercomputing centers and whatnot, is to simply require that everyone run on a single node, or run on one node, or a whole node, or multiple whole nodes. I've actually heard of some that require, you can't run on less than 8 nodes because they only do big science, and they're not interested in people running little applications. The problem with this approach is that for us, we run a lot of engineering studies, which are basically, let's try this parameter and then a slight tweak and then another slight tweak, either in a Monte Carlo type fashion or in a blunt parameter sweep fashion. And for those cases, to take that and refactor that application into a traditional parallel application would be really expensive and fairly pointless, when in fact our users could just submit, say, 20,000 jobs. We have a couple of users who do that, and just say, okay, I'm going to write a shell script, spit out all the input files, and go. And with that kind of usage model, we can't just have people come on and give them, say, okay, you get you get this node. Well, then they're not going to be using, in many cases, 7 of the 8 cores on one of the 8 core systems. So that's not efficient. So that's a problem for us. But in general, it's actually a pretty good approach. And of course, the nice thing about it is it's really easy. Just tell the scheduler only give one person the access to the node, and everything's fine. But for us, we find it doesn't work. Yikes! That's an interesting typo. So another method which is commonly used is gang scheduling. Again, this is mostly applicable to traditional parallel applications, but you can actually do it at a smaller level. The idea is that you timeshare all or part of a cluster typically on a pretty coarse slice, often minutes or hours. Hours being more common, because paging in and out a giant application that's using all of the resources of the cluster takes quite some time, often tens of minutes for a big job. But the idea is simply that it's just traditional time sharing, except that on a much larger scale. The nice thing is that jobs can't interfere with each other, and also because they're interleaved, they can get partial results sooner. The downsides are this context switch overhead. It's amortized out if your system is well designed, but it's still very high in many cases. And probably the biggest drawback is that there's not a lot of generally available implementations. There are some around. You see them in conference papers and whatnot now and then, but there aren't a whole lot of general ones. So that's an issue. Or in some cases, you can do sort of brute force solutions where you'll send a sig stop to all the processes in the communication, and they just won't do anything. But actually, and then they'll get pushed out because they're not running, and their pages will get swapped out. But then you get strange behavior when you start back up. Your network connections may have timed out, or you'll have to wait for all your memory to page back in. It also simply doesn't work well for our small job mix. So we've decided that that's not really a direction we want to push in our environment. Another related approach is single application or single project subclusters or subclusters. Some national labs use this approach where they have a funding model where once a year or on something like that basis, projects apply for resources and they're given this many racks of computers, and they're pretty much theirs to do with. They can do anything they want with them. They can put whatever OS they want on them. They have to hire their own system administrators and that sort of thing. Other approaches are that you can say, okay, you guys get these nodes, and you can run whatever we're going to run the OS, but you can run any jobs you want. If you want to log in and run 30 processes on these 2 processor nodes, that's fine. Whatever works for you. And that could work well. The biggest issue is that it is very coarse granularity, and so with our job mix, it's not a great fit. Also, because we're not really sharing the nodes except on this very granular, annual basis or whatever period, it means that it doesn't deal well with resource spikes, and there's no way to recapture underutilized resources. So an example of that would be if you have an application which uses, say, a single core but a lot of memory. You might need a fairly large node in order to get your 16 or 32 gigabytes of RAM, but you only have a single-threaded process. It's fairly common. One example would be something like running Nastran, where you have to pay for every CPU you use. It's much cheaper to, in many cases, or sometimes it's the only affordable option to buy single CPU licenses, and you have to buy a lot of cores just to get enough RAM in the system. But in that case, it would be nice if you could then run some other jobs that used the other cores and to take advantage of them that didn't need all this memory. So we'd like to be able to do that, and this subcluster approach doesn't really solve that. Another related approach to that is to virtualize the cluster. This is sort of the cloud computing model, where each job would run in a set of VM images. The big thing about those is that since each job is running in its own operating system image, and the virtualization frameworks are definitely designed to do resource constraints and keep those well isolated from each other, so it can be a very effective isolation method. And users can tailor those nodes to their needs, so their images to the needs. So you could be running in one set of experiments, you could have a full X installation and a bunch of big applications so that you could do graphic output or that sort of thing. And in another one, you could have a very stripped down image that where you're just running computation. You just need to do a little I/O, and that's it. Another nice thing here is that you can recapture some of those underutilized resources. So if you can have one big VM that takes up most of the system memory, but only has access to a few of the cores, then you could have other ones cycle stealing, or you could have where they're background tasks, or they could be actually allocated those cores directly. The downsides here are that the isolation is incomplete because the hardware is in fact still shared, and the isolation methods are good but not perfect. Users can still interfere with themselves within their own nodes, which you might or might not care about, but it's an issue potentially. There's also it's not a very good way to isolate small jobs. If you have a little job that's just cranking away and doing small evaluations of say a Monte Carlo simulation, it's pretty expensive if you then bring in a whole kernel and a whole operating system and have to maintain that in that case. There's also significant overhead. Typical estimates are in the 5% if you're really lucky to 50% if you're not, depending on what you're doing, what your I/O needs are, and that sort of thing. Continuing down this line of sort of virtualizing resources, the virtual private server approach. This is what done a lot in the internet, in the ISP businesses. It's how many if you get a shell account that you can do web hosting out of in your root, but usually you're running in something like a FreeBSD jail or one of the many Linux implementations or a Solaris container. This was sort of developed kind of pre-virtualization as a lightweight approach to solve a problem that hosting providers had. And it works very well in that environment. We think it's a possibly interesting approach in a clustered environment because it's small overhead, which was originally designed so that you could put, say, 100 or 1,000 of these on a single machine. For us, it's nice because it means it's not getting in the way. You don't have the overhead of multiple kernels, and those types of overhead. So it can be practical for small jobs. You still have potentially the ability to tailor your images to jobs, so you can have a lightweight jail or a heavyweight jail. Potentially, you could have different operating system versions running in different jails, as long as they're compatible with the kernel, and that sort of thing. And you also only virtualize what you need to virtualize, which again reduces the overhead involved. Downsides, again, it's incomplete isolation, and it's in fact quite a bit less isolation than you would typically get from full virtualization. One exception to that might be for instance, the Solaris containers model, where they've have schedulers and CPU bindings and all of this built in. But traditionally, it's much less isolation than with a full virtualization system. There's also reduced flexibility in that, for instance, on FreeBSD you could run a jail that had different versions of FreeBSD in it. You could potentially have 32-bit and 64-bit depending on your needs, but you certainly can't run Windows in there. You could run Linux, for instance. Stepping down into an even lower, or an even more basic set of isolations is to use classic Unix-like isolations. Most batch schedulers already support some form of these. They'll typically allow resource limits, and they'll automatically create temporary directories and that sort of thing, so that people can't interfere with each other. So a lot of these things are already there. Most Unix-like OSs support some form of quotas. They support CPU affinity these days, and you can also use memory disks, for instance, to partition file system space. There. So one of the pros is that these already work with existing. Many things are already implemented in existing schedulers, at least partially. Also, it's fairly easy to add new features because you're just exploiting operating system features. You're not trying to build an entirely different environment. So you don't have to, for instance, deploy an operating system image to run a job. Downsides, isolation is again incomplete. There's typically no unified framework for handling this and bundling the jobs together. Some exceptions here. Probably the biggest one is IRIX has actually a job a job ID which sits somewhere. I think it's somewhere between the process and the session layer, if I remember correctly. But essentially, it's a collection of processes which have resource limits applied to them and that sort of thing. Historically, resource limits would only apply to an individual process, which doesn't work so well once you start to have a parallel job that forks. So schedulers will do things like they'll set the resource limits, but then they'll watch all of the processes within a job and check their totals. And if they get too high, then it'll kill them off or take whatever action the administrator deems appropriate. One other issue is that there's typically no limits on bandwidth type resources. Things like network bandwidth, where it's either there when you ask for it or it's not, and then it might be available then later. Whereas things like disk, you use them up and they stay used until you free them. So typically limits work for those sort of things and not for bandwidth type things. So now I'm going to talk a little bit about the experiments we've done on fellowship. So we felt that we needed a solution that handles our wide job mix. And so of the main types that we looked at, we looked briefly at single application or project clusters. Because of their full isolation characteristics, we think that probably the only way to do that practically is some sort of virtualization system so that you can swap things in and out quickly, or relatively quickly. But we felt that it probably wasn't going to be a good option for us in general because of the small jobs issue. We've also looked fairly extensively at using more resource limits and partitions, and in fact, the actual experiments I'll talk about are all of various resource partitioning types. The nice thing is that they're easy to implement, and they can achieve some useful isolation without a big effort in systems development. We're also interested in virtual private servers. We think that's going to be a pretty powerful approach, but we've not done that yet. The nice thing is that we think that much of the infrastructure that we'll need to develop to do resource limits and partitioning will be applicable to the virtual private server functionality. So the way we implemented this is that in Sun Grid Engine, on each execution node, there's an execution daemon which always sits around and waits for requests from the scheduler. And then when a job is started, it creates a daemon called the shepherd daemon, which keeps track of all the processes and reaps the zombie children and that sort of thing. So it's responsible for all of that. It also handles many of the resource limits and is responsible for checking that for accounting. So it looks at all of the processes and determines how much resources they've used, periodically scans them to see how much memory they're using, that sort of thing. It also forwards signals to children and is involved in starting remote job components. So there'll be one shepherd running on each node that's part of a job. Our original plan was to modify this shepherd daemon to implement restrictions directly. And we thought we were going to have to do that. Fortunately, it turned out actually that we don't, because the Grid Engine framework allows you to easily substitute a program to run in place of the shepherd, and then we can wrap the shepherd up in this program. So we've implemented a wrapper script. It supports pre-command hooks that we run pre-hooks before we start the shepherd. It supports wrappers, so things like the environment command, which just exec the next command after changing the environment a bit, and then post-command hooks. And I've implemented it in Ruby because I like Ruby. So the first thing that we've implemented as an isolation is memory batch temporary directories. This solves a problem that we've had on and off for ages, where users will come along and they'll be using temporary files on the file system and on the drives in each of the nodes, and they'll run them out of space. And then other users will come along, and if they're lucky, they'll notice that they're out of space, and they'll get nice error messages back. But often they'll get really strange error messages. For instance, if you run PVM, the parallel virtual machine, it attempts to create a Unix domain socket and then tries to use it. And in some older versions, it wouldn't check whether or not it succeeded properly, so you'd get all sorts of strange errors if you couldn't create a file in temp. So the Sun Grid Engine already implements some features to help with this. The main thing they do is they set the tempter environment variable, which any well-behaved program that uses temporary file space will use, and they create a directory for each job, which is destroyed at the end of the job. And that works quite well. Unfortunately, normally that's just created in a directory, so you can still fill the whole thing up, and if somebody else is trying to run on the node, as we do a fair bit in our environment, they won't you can still have that directory run out of space. So our solution here is that we're creating memory-backed file systems that we mount over the top of that directory, and that's where users have their temporary space. Because we're creating a memory-backed file system, we allocate a specific amount of space for each job, and once they're out, they're out. As a bonus, this means that the temporary space is in fact in memory rather than writing to the file system, and so applications which use small amounts of memory, relatively small amounts of temporary storage, will see improved performance. So a quick demonstration of how this works is, so we have an example script here. It just shows it's an example job script that just shows the temporary directory. I submit the job, and then here's the output file afterwards, which shows that there is this temporary directory and shows that it is in fact a file system mount point with memory allocation. Users can in fact, in our implementation, users can use a resource called temp space to request the amount of space they get. I have some attempts to construct an actual memory file system which has about that much usable space, but how effective it is depends on the size. I haven't quite figured out all the magic variables involved in producing a UFS file system with a particular amount of free space. So that's all well and good, and that's something we intend to deploy fairly soon because of both the performance and the isolation benefits. But there are badly behaved programs out there that go out and use temp/temp directly because they have it hard-coded in rather than using tempdir. And so we looked for a way to solve that problem because then badly written applications can still go hog these shared directories. So we decided that what we wanted was to have per job temporary directories, meaning basically virtualizing portions of the file system namespace, or of the file namespace. And the approach we've chosen here is to use variant symlinks. So a quick introduction to variant symlinks. Variant symlinks are symlinks that contain variables which are then expanded at runtime, which allows processes to have a different view of the file system namespace. So a simple example here, we have a couple of test files, and then you create a variant symlink which has this, in our case, has a shell type syntax where there's a variable, and then there's variable name, and then a default value is possible, similar to it in SH. So if you look at the file by default, you get one set of contents. With the variant symlinks, you can get different sets of contents. So it provides a simple method of virtualizing the namespace. In our implementation, and then a little more about our implementation. It's derived from the implementation that's in Dragonfly BSD, but it's changed substantially. The biggest thing is that we've taken the scopes, which are system privileged process and and then user changeable per process variables. And in Dragonfly, they've also have a jail scope and user scope variables override system scope variables. The problem with that is that if you think about, say, a variant symlink to, say, /lib. Now, if the user can set what that value is, and you have a setuid program which evaluates a library, then that setuid then you can change what code that setuid program runs. Now, there are obvious ways to solve that. For instance, don't pay attention to user set values in the case of a setuid program, but at the end of the day, it's fairly easy to make mistakes in reasoning about how all these things interact. So I decided to go and reverse the order so that it was easier to not make mistakes. In addition to scope, we're using let's see. So yeah, in addition to scope, I'm using % instead of $ to avoid confusion, so it doesn't look like it's a shell variable. In particular, because we're going to use common names. For instance, for the /temp implementation, we're going to want to set the tempdir variable, which is what you expect in the shell. And so I think it's best to have the namespace be clearly disjoint. I also added the default value support to support things like temp, where you do want it to work for processes that aren't part of the job, and for that to be a consistent space, because there is an expectation that things can rendezvous through things like Unix domain sockets in temp. I've also added login.conf support, and we use I don't set any automatic variables, similar like the AFS at system type. One of the other reasons for using the % is that it doesn't conflict with either the AFS or the NetBSD variant symlinks, which are all automatic. And currently I don't allow the setting of variables in other processes other than the current one. That's probably going to change. So that works. I've not actually set up a command script for it, but this stuff is mostly complete. Hopefully I'll get it in time for 8. The next type of isolation that we've looked at are using CPU sets. Jeff Robertson implemented these in FreeBSD 8, and then John Baldwin ported them back to FreeBSD 7, so they're in 7.1. So a little bit of background on Sun Grid Engine. In Sun Grid Engine, there's this concept of slots, and each execute host has one or more slots. By convention, there's one slot created for each core on a machine. It doesn't have to be that way. In a number of environments, people create vastly more than that and allow the machine to be oversubscribed. But in the case where there is one per CPU, you might expect that when you got one slot, you got one CPU, but in fact there's no enforcement, because there is in fact no inherent relationship. So each job is allocated one or more slots. A single process job gets one slot. A parallel job gets multiple slots. What we're doing is we've written some scripts to use CPU sets and tie them to slots, so that when a job runs, it's actually tied to a specific CPU set. In our current algorithm, we just store some allocations in a file in var, and then we have a naive allocation algorithm which just tries to find the largest contiguous set of CPUs and attempts to minimize fragmentation of the allocations. That's not really ideal. Ideally, we'd like to be able to ask for either CPUs that either share a cache or don't share a cache, depending on the nature of the job and the algorithm. But right now, we just have a simple allocation algorithm. For this one, I've got some benchmark results. We used a 8-core Xeon with a fair bit of RAM in it, and then ran a simple integer benchmark that I dug out of ports. It's the n-queens problem, where you place queens on a chessboard in a manner where they none of them can capture each other. And then I used 2 different run cases, one which runs for I think that runs about 20 minutes on this machine, and then a smaller run that runs about 5 minutes. The load one runs in the background and just generates noise, and is either I run too many of them and contain them with CPU sets, or don't, and then I run the other one multiple times to get valid measurements. So a quick summary of the results. So first, with a baseline run, we ran the benchmark number once, or I ran it 8 times and then took the average values. And that was just by itself with no additional load on the system. I then ran it with 7 load processes. So in principle, it should get about the same amount of CPU, and there shouldn't be any interference, because, well, they're all using CPUs. There's nothing else to be done, and they don't use enough memory to consume to have any contention there. And then with 8 processes, this is sort of the badly behaved case, where you have an application that spawns n CPUs worth of threads, when it wasn't supposed to be. And so here you see the expected performance drop of about an eighth. In that there's another process in the way. Now, then I went and did the same thing again, but with CPU sets active. In that case, you can see that we have no significant difference between the baseline case and the case here. That would be expected. One nice thing is that we in fact have no statistically significant difference, whereas before we had a small amount due to the fact that in the baseline case the process would not have significant interference from system tasks. And then in the 8 CPU case, or the 8 load process case, we again see no statistically significant difference. So CPU sets are in fact properly containing the set of are properly containing the processes, which is nice to know. One thing that I don't have on here is actually when I initially did some runs where I just did the baseline case but also stuck it in the CPU set. And in that case, I actually saw a slight performance drop when I was using the first version of the allocation algorithm. Turns out that was because the allocation algorithm was binding the process to CPU 0, which ends up getting a fair portion of kernel tasks run on it, and as a result, it actually slowed things down. If you flipped it over and ran it on a different CPU, then you again saw no difference and just a slight tightening of the variation. So, some conclusions of future work. I think these are useful proof of concept isolations. I'd like to implement more of these down the line, more things like this, tighten that up, and really like to get the framework that I've written out and released into the public, but haven't been able to polish it up and get it through corporate approval yet. I think in the future that virtual private servers will be another interesting approach. Some conceptual things, for instance, being able to run a Linux environment, so it looks to the user like they're running, say, CentOS, and they can run their commercial Linux applications in there. But for performance analysis purposes, you could run dtrace on those applications. So that would be pretty cool. Another option would be to be able to run both 32 and 64-bit user spaces depending on the application. So if an application needs a lot of pointers, but it fits in about 4 gigs of RAM, it'd be more efficient to run it in 32-bit mode rather than 64-bit mode. Whereas another application might need more memory and therefore would be better off in full 64-bit mode. One other potential use here is that we could upgrade the kernel to get performance enhancements, but allow users to continue using an older user space on top of that in their particular jobs, and then they can upgrade when they wanted to. And that would make a lot of my users quite happy. So that would be good. I think another area of interest is it would be nice if we could have limits on things like network or disk bandwidth. It's fairly hard to implement limits on, say, well, it's fairly easy to do things like isolate the network bandwidth from a particular application, but then when you throw NFS in the mix, it gets quite complicated because you don't know which processes are responsible for that NFS request unless you actually trace that down in the kernel and add that functionality all the way down. I did see many years back, someone I believe from Japan posted some bandwidth, sort of a nice for network bandwidth that did some of this stuff, at least for the socket side, and it'd be interesting to see something like that revived. It'd also be interesting if somebody would add something like the IRIX JIDT to the system. That would be helpful, I think, and be a fairly straightforward application, so that it would be possible to say, give these processes a resource limit, instead of give this process a resource limit and its child an identical resource limit. So I think that would be quite useful, and probably actually a good summer code project now that I think of it. So I think those are future areas I'd like to look into. I think would be useful. So, any questions? Well, thank you all for coming.